If you've ever dismantled a Rubik's Cube and reassembled it, you probably got an unsolvable one. Unless...
Actually, you have a 1/12th chance of success since there are 12 different kinds of cubes if we only consider face turns. Where did that come from?
Counting seems trivial, but it can get complex.
One example is to count the number of distinct objects with symmetry taken into account. Here's a 2x2 table to be painted with red and blue. How many distinct colorings are there that cannot be rotated or reflected to match one another? Well, we have 2 color choices for each square. That gives 16 colorings. But wait, some of the colorings can be transformed to match one another. In fact, there are only 6 distinct colorings. Instead of manually counting, we can turn to Burnside's lemma, a useful result in group theory.
Let X be the set of all objects, G be the symmetry group whose elements are transformations acting on the set X. A fixed point of X has an element in X that is unchanged by a group action. Let's find all the fixed points. Under identity, there are no changes, so all 16 objects are fixed points. But for other transformations, not so easy. For the 180-degree rotation, the fixed points need to have matching diagonals, so the bottom 2 colors are locked by the top 2. That makes only 2 squares for free color placement, meaning 2 to the second fixed points. Following the same logic, we can count the number of fixed points for all the other transformations.
Burnside's lemma states the number of orbits, or distinct objects, is the average number of fixed points of G.
Here, 48 fixed points, divided by the size of G, which is 8, gives 6 orbits.
Burnside's lemma is very handy for counting orbits in real life.
You can use it to find out that tetrachloronaphthalene has 22 isomers.
Next time, when you try to reassemble the Rubik's Cube, don't do it randomly, because now you know your chance of success is very slim.